Good morning. Welcome everyone to the EasyPower Tuesday Refresher. You're welcome to contribute to the discussion by submitting questions or comments during or after the session. Had a complaint last week that I didn't leave the session up until everybody got their comments in, so we'll try to be a little bit more polite this hour or this half hour. Today we're exploring the specific topic of modeling photovoltaic elements in EasyPower. And as usual, we start each session with a poll question, and we invite you to participate to help steer the presentation, as well as provide feedback to our development team for the types of applications that people use EasyPower for. And today's question are going to be basically, how often do you include a photovoltaic system and what's the common size? So if you would please help us with some feedback and your responses here. The more feedback, frankly, the better it is for our understanding. In some regards, we get inputs literally every week for feature enhancements of the tools, and without the ability to understand what part of our user base the requests pertain to, it's difficult to prioritize some of those requests. So appreciate everyone participating. Here's how the responses looked. And then the second question is that how large are the systems when they're included in your project? And at the end of this presentation, I'll actually have a couple example files that we reference in the manual, but fall short of providing the actual development database. And for those of you that would like a copy of it, by all means, we'll provide a feedback element to give you access to those systems. So I appreciate you participating in this. Here's how the responses looked, and let's jump into the rest of our presentation. So what we're going to cover is, in essence, the very basics about photovoltaic systems, how that pertains to and how we model the systems in EasyPower. And then, as I mentioned, we'll go through a couple examples and show some typical analytical capabilities both in short circuit and PowerFlow. And by all means, if you'd like a copy of the files that I'm going to be illustrating or showing, just let us know. So without a whole lot of concern about people opposing this opinion, just by the amount of reports we see in the media and in technical journals, the growth of photovoltaic energy generation is steadily increasing, and these are ranging from small commercial systems included in new building design, ag-related installations, and then those, I think, the installations that receive the most attention are the large utility scale systems, many of which are in the Southwest desert. And it's all harkens back to the lowly PN junction. Without belaboring the point, the heart of the PV system is the lowly PN semiconductor junction, and when it's properly designed and constructed, the junction, in fact the whole semiconductor wafer, can be utilized as an energy converter. So when the solar cell is exposed to sufficient proton energy, it will generate a number of electron-hole pairs. When connected to a load, the electrons will leave the cell as current, and as the electrons return from the load, they will recombine with an available hole in the silicon matrix, and the process continues. Now, during this process, the electromotive force of approximately 0.6 volts is generated, and it's more and more becoming an efficient way to generate electricity in terms of the cost of producing these PN junctions or these wafers. Now, based upon making an array of these solar cells and wiring them in certain configurations, a fair amount of useful electrical energy can be generated. And as we characterize what a cell or an array can produce, there are some common elements that arise. And by overlaying the IV curve, the current voltage curve with the power versus voltage curve, we can predict some parameters that are significant relative to both designing with these energy sources as well as modeling their performance. And I'm referring specifically to the peak power of the power voltage curve. At that intersection with the IV curve, we identify that as the voltage of maximum power and the current for maximum power. At the point where we short the output of the cell and measure the current generated, that's referred to as the short circuit current, and the voltage at which is generated when we have the circuit open or no current drawn is referred to as the open circuit current, or open circuit voltage. Now, the spiffy thing about PV junctions and cells is that they can be essentially arranged or connected as batteries. And when you do this, you identify these same voltage and current parameters for the overall combination of cells, and very much can regard them as batteries. So if we need additional amperage, we put more cells in parallel. If we need additional, or we want to generate more voltage, we put the cells in series. But in every case, we'll have a current and a voltage identified for both max power, short circuit current, and open collector. Well, you put all this into practice, and what you'll see from a manufacturer is a performance chart, if not just a list of these specific parameters. And very frequently it shows up as a parameter list rather than a graph. But in any case, you're going to want to be able to identify the voltage of maximum power, the voltage at the open circuit, and the short circuit current for the system that we're using. When it comes to putting that model into EasyPower, we simplify the results, or we simplify the model in terms, and frankly it ends up being very similar to a battery, but we'll have the ability to generate a current at a varying voltage level into a short, and then a voltage at a zero current level. So this is the voltage that's generated into an open. And then overall, the maximum power that the cell can generate is a product of these two parameters. So if we take a typical spec from a manufacturer, we may be able to identify these values and then utilize these as we're correcting or constructing our model. So in this particular case, we've identified the voltage of maximum power as 33 volts, the open circuit voltage as 40 volts, the short circuit current as just under 8 amps, and then the maximum power output is a product of the voltage and the current at maximum power. So that's what we're going to see when we get into the EasyPower tools. Likewise, there's a need to deal with the inverter setup, and that becomes one of essentially converting or verifying the power output capability of the inverter and then matching it with the model. Currently, we just use the IGBT model because the thyristor hasn't been completed yet, and this is an inverter model that we use actually in other elements as well. So let's try this out. We have a manufacturer's data sheet here for electric photovoltaic module, and we see on the data sheet that there's a P-max rating, and we're going to use this right-hand column of 250 watts. It's got an open circuit voltage of 37.6 volts and a short circuit current of 8.79 amps, maximum voltage of 31.0, and then a maximum power current of 8.08. So from all of that, we can utilize in calculating EasyPower. So let me jump into this and launch EasyPower. Now what I'm going to do is build a hypothetical module using the parameters, or that component that we just identified from Mitsubishi. And the way we're going to do that, if you'll pardon me just a second, is to construct an array that we're going to refer to as a 10 by 10, because that's, again, hypothetical, and that's the power that we want to generate. So all right, so what, and again, this is all hypothetical, has nothing to do with how you would want to design a PV system necessarily, but we're going to use the parameters that we took off the data sheet, and we're going to build a 10 by 10 array, and that means the voltage that we're going to, the power is going to be 100 of these units. So the maximum power for the system is going to be 25 kilowatts. The ISC, or the short circuit current, is going to be 10 times the current of a single cell, because we're putting 10 of these in parallel. So the maximum current at short circuit will be 87.9 amps. And then the voltage at open circuit will be 10 times the voltage of the 10 elements that we put in series, which will be 376, excuse me, 0.376 kilovolts, and then consequently the maximum power is going to be 10 times the elements of voltage in the current. The voltage at maximum power, I'm sorry, is 310 volts. So to model this in EasyPower, we open up the array and pull it in from the other screen, and we get this dialog box that we use these elements. So the maximum power rating is going to be 25 kilowatts. The maximum current is going to be 87, ISC is going to be 87.9 amps. The open circuit voltage is going to be 0.376 kilovolts. And then the maximum power voltage is going to be 0.310 kilovolts. Now we need to connect this to some sort of load. Again, I want to bring my elements in from the DC equipment, because this is generating DC. We're predicting that our bus will be approximately 300 volts. So let's kind of zoom in a little bit. So I've set up a cable, a 10-foot long cable, 350 kcmil, to try to minimize the resistance here. And we're predicting that the one-way current's about half an ohm. And then we set up a load of roughly 25 kilowatts, so that at any given point it's putting out somewhere near the maximum power. So first thing I want to do is to go into PowerFlow, solve the equations, and what we see is that the voltage at the bus is slightly higher than what we predicted. There, our current, our maximum or optimum current is here at 27 amps, and consequently we're producing, looks like we're showing the current. If we look at our PowerFlow one line output, in our branch flow, let's just say kilowatts and kilovars. So we're putting out just under 27 kilowatts. Now, we're probably just as concerned about, so it looks like the model at least works as we'd expect any battery would in these conditions. And we'd also want to anticipate or look at the short circuit current. So if we go back to our short circuit module, fault the buses. In fact, we see the 90 amps at short circuit current, which is just under the 87.9, just over the 87.9 that we predicted. I suspect this is rounding error because I have it set up to 2 significant digits. And this actually brings up an issue I had last week when I was talking about the VFDs. When we have a low current such as this that may not trip a protective device, it won't necessarily give us an arcing current or an incident energy calculation on any bus. So in small systems or in segments of systems where the current is this low, we may not see calculated incident energy. Now, so this is something I invite you to play around with and get comfortable with the fact that you can model any size array that your system may require. And from there, let me kind of jump into some examples and then the larger scale designs or one-line designs that we reference in the manual. If I go into my sample file that you should have in your tool design, there is a photovoltaic system there, and this is a relatively small system, but it does allow us to look at the general function of the module. In these cases, so this is not too dissimilar from what we just generated. This is a 40 kilowatt panel or an array with 67 amps and 660 volt generation. If we go into short circuit, fault the buses. So I haven't talked about the inverter yet. And this shows that even at the current we have, and probably because of the current, we're only talking 67 amps, there's relatively high calculated incident energy, and we can see that as a result of, if we look at, say, one bus at a time, at the total, we're seeing a total bus current of, or arcing current of 267 amps, and a maximum timeout on the calculations of 2 seconds. Again, that's where you need to use your engineering judgment to ascertain whether that's adequate or if it makes sense to maybe lower this time so that a more realistic energy is produced. Let me jump back and talk about the inverter real quickly. Part of the system is going to be the inverter, which is going to be able to carry the energy back to the AC side. And here we've got the basic elements of the size of the capability of the inverter. We calculate the X over R, and then based upon the fault current that the manufacturer suggests and the fault time, we set up the current trip time or the maximum calculation time for energy upstream. So again, as we go back and fault the system, we'll see results here. If we fault this bus, that the tripping device in this case is the fuse. If we open the fuse, we see that we have a more modest incident energy, and it's as a result of the protection time that's predicted by the inverter, which is the 0.2 seconds. Again, when we go back on the DC side, this is controlled by the maximum current which is set up under the short circuit. That's a good point. Where are we going here? So this is a 2-second time that's being limited for these calculations. If we decide that, well, in reality, this current won't be as dangerous as this 4 calorie level we're predicting, one alternative to dealing with that is going back to this bus. Let's go to the bus and open up the dialog box. Go to the Arc Flash tab, and here we say, well, I think, and because we only have a couple hundred amps, that I would be safe in predicting a half-second maximum time for an arc to exist, and the results of that would show up now with a more civil 1.2 calorie PPE requirement. And now as we look at the results on the Arc Flash hazard spreadsheet, we can see that 0.5 seconds is what's being used for the calculation time. Okay, again, I don't recommend anyone that you be cavalier in these considerations, but when we're talking about a maximum of 200 amps and a voltage of, I think it was 600 volts, that is dangerous, but it's not an arc that will last 2 seconds. In fact, in my estimation, it would last considerably less than 1 second. Okay, hopefully that was helpful. Before I digress or get too far off the beaten path, let me take a second to open up the other 2 examples. So this particular file is inside the sample folder of every installation. Some people like, one of the things that I do just in terms of a demonstration is I save an array where I'm demonstrating the ability to generate a PV string of a certain dimension that I can then use over, oh, did I lose it? Yeah. That I can utilize and construct multiple segments for an array using systems that I'm familiar with or that may be more frequent in the design. Part of that ability to save a system like this as a subsystem is valuable when we have very large arrays or we have projects that use the same components time after time. So to that end, in the data book, in the user's manual, we have some system we refer to 2 different systems. One is a large array.des and the second one is a large system.des. And there was an intent to make these available on a web link, and I think the web link got archived. So this is one system that I think is valuable in seeing how the system was set up, but in essence it's an array of 2.7 kilowatt, 7.5 modules, and 4 different collectors, and all run through a transformer to generate 480 volts at some significant current. The other, and again, just let me know, contact me, Jim at EasyPower.com, or leave a comment on a question sheet or question box, and I can send you a copy of this along with the other example, which was the large system. I guess I need to go back to one I opened recently. So this is a large array, and then the other is a large system. Same type of thing, different elements where a larger system is being built. And in this case, it's not quite as symmetrical. but it does reflect some different topography, and the main differences being where we put the inverter and where the transformers are located, and then how that is summed at the bus level or at the collector level. And this ends up being, well, and so this actually also makes another point. If we go into the short circuit focus, fault the buses, and look at incident energy, we can see that on the individual buses or individual feeders, we have relatively low energy, but when you sum them and take the voltage up, we're talking about more substantial incident energy calculations, and it's worthwhile noting. And here I didn't generate the arc flash hazard spreadsheet, so let's do that. And so here you're seeing that we show a maximum trip time of 1/10 of a second. We're on the collector bus. We're still showing 1/10 of a second, but it's considerably higher energy because it's all being summed across the different feeders. So, not that I wanted to go much further into this, but certainly I think I enjoy this because it's relatively simple. It makes a lot of sense. And once you have it down, you can reuse it without having to recreate the wheel every time by generating your base matrix and saving it as a subsystem. And so it's like a triple bagger in terms of showing off the benefits of EasyPower. I think that's all that I have as far as information. I'm going to check to see if we have other questions or comments. And as I say, the two files are available. You can either contact tech support or me and be happy to give you reference and copies of those DEZ files. Appreciate everyone attending, and I will look at my list of questions here before we sign off. If I don't get to all the questions online, we'll answer these by email.